There we go. So, good morning, everyone, and thanks for coming. We are quite little people, but it doesn't matter. My name is John. I'm a worker at Tekniker. We are an R&D center in the north of Spain. And I guess you may already be wondering, if we were going to talk about functionality, why can we read the word process industry in the screen? Let me explain it to you. There are several reasons. First of all, Tekniker belongs to AdMa, which is the Partnership for Processes for Planet. If you are not familiarized with the word process industry, it's that kind of industry that somehow produces semi-finished products. I'm talking about metallic alloys, plastics, textiles, paper. It's something that it doesn't directly come to us. It needs a little bit more elaboration. That's called manufacturing. But maybe the easiest way to get familiarized with process industry is that icon we can see right over there. You know that old factory with the chimney and the smoke? And it's not far away from reality. Indeed, process industry is by far the greatest consumer of energy and materials in the world. But from the other point of view, it's probably your main customer as material designers. If one day your great substances or materials end up being commercialized, they are going to be the ones that will upscale them and really make money out of it. So let's talk about safety and sustainability. Remember that SSbD is a framework not only for materials and for substances, it's also for products and processes. And indeed, it's something where everything can work together. If we have a look at this diagram, we will see that process industry is somehow involved in the area of step number 2, safety in the operational environment, sustainability, and finally, the socio-economical assessment. Today, I'm going to talk especially about steps number 2 and number 4. So, step number 2, safety. I brought here 4 examples about how process industry can improve the safety of the materials or the substances we want to elaborate without changing their chemical composition. I did it intentionally. So let's start with the first example. Let's talk about the material format. I'm not sure whether you've ever been working with additive manufacturing, but something you should know is that if you work with aluminum powder as raw material, it's an explosive material. And at this point, well, we could directly start trying to redesign the material looking for non-explosive properties, but it's much easier than that. I told you that aluminum powder is explosive. We can just change the format of the material and work as wire. That's called wire additive manufacturing, and it's not risky at all. Another example, probably in the same line, is whenever our process needs secondary substances that are not intrinsically part of the material itself. I'm talking about, for instance, lubricants or solvents. In those situations, again, it's not about substituting those lubricants or solvents. We should somehow go deeper in the process. I was quite surprised a couple of days ago when we were in that group for lubricants, and Iranzu, she was the first one who said, do we really need those lubricants or those solvents? That's the right question we should do ourselves, because sometimes we can drastically modify the process in a way that we don't need them no more. That's the case of coating. A lot of industrial processes are based in conferring advanced functionalities to materials just by coating them. If we start thinking about different processes like physical ones where solvents are not necessary, we can directly remove the problem from its roots. All right, let's go to the case number 3. This is when it's not the material, the one that is hazardous, it's the process itself. For instance, thermal processes of metals. We need to increase up to 1,000 degrees the temperature of the material in a furnace. And that's something relatively risky, especially in the case of quenching, where we have to heat up the material, take it out of the furnace, and then instantly introduce it in cold water. Don't do it in your home. So in those cases, something we can still improve is to ask ourselves, that new properties that we are looking for, are they dedicated for the whole material, or do we just need them in some areas of the material, like the surface? If that's the case, we can move from bulk heating to just surface heating with technologies like laser, which really minimizes the hazards and the risks. And last but not least, there will always be situations where that hazard is very difficult to remove because it's something inherent of the material or the process. Then we can always change the working environment. And during the last few years, it's gaining the attention of research, the idea of machine-human interaction. The idea behind it is somehow to convert sensors or cameras to the processing machinery in a way that they can detect the presence of humans in the surrounding area. If the machine considers that someone is very close to the risky area, it will automatically stop. And that's just about redesigning the processes to be safer. We will for sure need data. And for that purpose, I've got good news. In process industry, we have access to a huge amount of theoretical and real data. On the one hand, we have very good analytic models like finite elements to somehow simulate how the new processes will behave, how much material they will need, how much energy we will need to input. We can also simulate very well the way that the risk propagates in the company. I'm talking about radiation or heat. If we are still working with toxic substances, we still have obviously the QSAR models. And something that I wanted to highlight, process industry usually works with digital twins. This is a huge source of real-time information. I'm talking about information about material consumption, material flows, energy flows, even people working around the machinery. But that's a dragon. As Irina yesterday was saying, it's quite difficult to get access to that digital twin of the company. So don't be dragon, share your data. Right, let's move to the next step, sustainability in process industry. In the case of processes, the strategy for sustainability is quite clearly defined. There are like 7 or 6 spots where currently the industry is working. I'm going to start mentioning the first 2 ones. They are quite similar. It's material and energy efficiency. The idea is almost the same. Save as much material and as much energy as you can. And currently, the main solution seems to be in the area of digitalization. It's a word that I really don't like to use because it's so broad that it can be confusing. But in this case, it's just about monitoring all the material and energy consumption we are having in our company and detect those areas where we are really wasting energy and material. In many cases, it's just about switching off the machines where they are not being used. Another trending topic in process safety is somehow to change the main source of the energy. We still have nowadays a lot of industrial companies that are using fossil fuels for their processes. I'm talking generally like thermal processes, like casting. I'm going to be honest, it's quite difficult to convince them to change that because it's somehow the heart of the company. But there are alternatives. There are always green alternatives like green hydrogen, biofuels, or even think about whether we can move from burning things to somehow electrify the process in a way that we can get access to renewable energy. And the fourth option is just to think about the process, including the whole life cycle of that material, and even to introduce circular strategies like reusing, remanufacturing, recycling, etc. And I wanted to stop for a while in this last slide because it's actually the bridge between processing and functionality. I brought this simple example, but I think it's quite significant. Imagine we are trying to design a new material, let's say a metallic alloy. For the part you are seeing in the picture, that's a connecting rod of a car. And the functionality we want to confer is durability. I mean, we want it to last for a very long time. Indeed, our functional unit will be that that part has to be driven for 5 million kilometers. It sounds crazy, but actually, if we consider remanufacturing strategies, it's not very far from reality. So, what's the matter? If we start defining or designing a new material with an extreme high durability, we will notice that things are never for free. Hard materials usually need a higher amount of energy during the production. And indeed it's even worse. Once that we produce that hard material, it's going to be quite difficult to manufacture a part out of it because no one can drill it, no one can bend it. I mean, it's a very difficult material to work with. So, question, how do we know if we are doing something for better or for worse? Well, the answer is LCA. We have to have an overall overview of the whole system. But before leaving the floor to Francesco, who will talk about these functionality things, I just wanted to remark or highlight something. It's fundamental to have a clear idea and a clear numeric and measurable idea of what's the functionality we are looking for. Otherwise, we could end up defining or designing a material that, even being wonderful in terms of functionality, it's not sustainable, nor economically, and nor environmentally. Thank you.
Do you want to ask something now, or we can wait for Francesco? Maybe we can wait for the whole presentation and then we have the questions. So Francesco Pagano is from Tekniker 2, and he's going to continue the presentation.
Okay, thank you for coming. Well, this is my first time presenting this kind of framework, so I will try to give you an overlook of what I intend as functionality, but after this talk, you are free to come and we can have an exchange of ideas, so that next time I will improve also. And we are in a school, so I hope that you can teach me as well something. So I will start just with the basics. And I know that there will be people that will not agree with this first concept of material. So what is a material? If we talk about an ideal material, we will say that it is a substance that is made by atoms that are combined together under a certain structure. So the way that they are combined can give some specific properties. Well, this is quite interesting because you can see that there are materials that are made just by one kind of atom, carbon, for example, and even like this, they can have completely different, different properties. So here we have diamond, that is the hardest natural material existing, and we have also graphite that are made by the same atom, but just with a different configuration of the structure that they create. In the case of graphite, they are layers that are bound by van der Waals force, and so they can slide one against the other, can give good properties as friction, low friction, and so on. We can have a carbon nanotube, different kind of structure, just with one atom that is combined in different ways. Well, this is very good for the modeling because it's quite simple to model this, but in reality, a material is composed by many other components. So we have a lot of chemicals that are involved. There are structural defects that are not considered in the ideal world. There are parts that are not homogeneous, and a lot of impurities. So, well, let's say that the world sometimes is more complicated. So we need to have an idea of how to create these materials. So we know that there are some characteristics that can help to give specific properties. So there are some microscopical level parameters that we can play with to give a specific functionality. We can also play with the composition, adding some alloys, for example. This is the case of the metals. Most of the metals are composed by different alloys that are mixed, or additives, like in many chemical products. We can also confer some properties by processing the materials. So we can harden the materials with heat treatments. We can also use mechanical treatments to confer specific properties. And then there is also the environment that can give defined properties to the material. So, well, how does this look like when we are talking about functionality? So when we have a material, we have to consider that the functionality of this material is the ability that the material has to behave in a certain way in a specific environment. So, and for a specific application. So a material can have a lot of properties, but it doesn't mean that this is a function of the material. Because, for example, a jacket can have some specific optical properties, but if I don't need them, it's not part of its functionality. So when we see a material, well, a determined material, we associate to this the properties that we want normally. So, for example, we want that a jacket will be warm, or from a sunscreen to have a UV protection. But in general, there are not just the properties that comes to our mind immediately, but there are other properties that we have to consider about, because it's not just one of the properties that make the material functional, but it's a combination of them. So, and a very important point is to consider the conditions that we have to test. If we want to characterize a material, we have to put it in a specific context, and we determine conditions, because otherwise we can assess the wrong parameters, and so we are giving a functionality that it doesn't have. So yesterday, 2 days ago, we were talking with some of you about the use case of lubricants, and I realized that there were some aspects that I didn't touch in my presentation, so I've added a little bit, just one part. So when we are thinking of material, we have to think about the purpose that has to be satisfied. Are we able to modify the material itself, or is better to find a different kind of approach, and so a different kind of solution? So there are we considering all the properties of the material in the right way? So I made this kind of like, I went back to the use case that I had proposed. So this is the use case of lubricants for deep drawing process. So, well, some of you didn't know this process, so I will tell that it's like a punch that presses against a sheet of metal and give a determined shape to the sheet so that it has a functionality. In this case, it's a basin sink. So what we expect from the lubricant in this process is to reduce the friction and to mitigate the wear, specifically, because in this process, since the metal is sliding against metal, there is a lot of heat that is produced, and so we need these properties from the lubricant to make it easier the process. So, well, if we are talking about our problem is that at the moment there are chlorinated paraffins that are an additive for the lubricants that are extremely toxic. So we want to substitute them. What is the functionality that they give to the lubricant? They are anti-wear and extreme pressure additives. They reduce the friction, so we can keep this in mind and so to find a solution for the substitution. They are also quite thermal stable, so these are the properties that we want from the lubricant because we have to substitute them. So we can think about the new solution. So should we just exchange the chlorinated paraffins with another additive? Should we make a completely new formulation? Or is it possible to have a new process? For example, a coating. It's a good solution. In many cases, it's used. So we could also think about this. We can go to the laboratory and start to test the lubricant and the coatings and see that we have, well, good properties from the side of the coating. It has a good coefficient of friction. The wear is low. It's much more stable from the thermal point of view. So it's a very good solution. We should apply. We can test with laboratory tests. We scale it up, and it works. But then we go to apply this solution, and it will fail. Why? Because we haven't considered all the parameters that were useful from the side of the lubricant itself, because the lubricant has also to dissipate heat. It's not that it has just to be resistant to heat. It has also to mitigate this heat and has to remove it from the component. Otherwise, we are accumulating heat inside of the die, and at a certain point, it will generate a failure on the pieces that we are producing, and also a failure of the die itself. So what I wanted to transmit is that we have to think that even if we are looking for the substitution of a component in a system, maybe that if we can change the process and we can adapt completely new solutions, but we have to look at a very big picture there, because maybe there are some aspects that we are not considered from the beginning. So a very thorough analysis is needed when we are deciding to change a solution. So, well, this was thanks to you that we were discussing about this. So, well, next point, the environment. When we are trying to see the functionality of a material, we have to consider always the environment. It's one of the most important points, because if we start to characterize something, but we are not trying to reproduce the real conditions, well, the material will behave differently. So there are effects of temperature. The chemical environment is important. Also, not the atmospheric pressure. If we are working vacuum or we are working at high pressure, we can have completely different conditions. There is a biological exposure that we have to consider. The radiation can affect the materials. And also, for mechanical systems, it's important how which are the loading conditions, the working condition itself, the movement that are taking place. So I have a couple of examples here. So this is, well, maybe that some of you have already worked with hydrogen. Now is a very, very appealing material, because it's a gas that can be produced in a green way, so it's very attractive. But it's very, very dangerous. No, well, of course, the first idea is that the danger comes from the explosion that can be generated. It's a flammable product. It's not just this. It's the hydrogen is very dangerous for metals and for other materials. So here there is a curve from a slow strain rate test that is like start to apply tensile stress to the specimen for a long time and wait to see what happens. And you can see that, well, the material, if you see the stainless steel 304, well, at a certain point with hydrogen, it fails. It's just very, very far from the maximum resistance that it should have. But the hydrogen enters inside of the structure, of the metallic structure, and that can cause a brittle fracture. So this is very dangerous in some conditions. So we have to think about the environment when we are realizing a test. There is a second example that I took from a YouTuber. He's a Veritasium. I really suggest you to watch his movies, his videos, because he's a physician that starts to explain different stuff. And there is one interesting video that is about the cold welding that can happen in vacuum conditions. So, well, in vacuum, nothing should happen, no? Well, that's also one of the problems. Because when you have two surfaces, metallic surfaces, that rub one against the other, normally they create immediately a passive layer. So in this moment, the material becomes passive and do not react. Again, for example, aluminum is very reactive as metal. So immediately there is a layer of oxide that is very, very thin, but it's there, and it protects the surface. If we are in space, there is no oxygen. So in that case, the metal can weld one against the other and stick together. So what happened there, it was a space mission, and at a certain point, a door was not opening. And it was impossible to open the door. And so they found this. Of course, in this case, it was difficult to predict this behavior. But that's why when we think about characterizing a surface or a material, we have to think of the conditions that have to be as close as possible as to the reality. So, well, to go from the characterization test to the functionality, sometimes it's quite difficult. This is what I learned when I was trying to characterize the anti-icing properties of a material. So how can you do with a test to reproduce what happens on the wing of a plane? So normally, you have also to try to be as close as possible to the reality, but with the means that you have. So in this case, what we do is like to measure the contact angle that is produced, that appears between a surface and the water, for example. Then we start to think about methods to measure how much force I need to remove the ice when it is formed. I can put cameras in a climatic chamber to see the time that it's needed for the ice to stick on the. There is a lot of work sometimes for functionality. Sometimes it's very easy. I just make a test and have the functionality. Sometimes it's not like this. So we have to think about this, and we have to try to design the right experiment for this. I know that this is a point that is quite, that goes against what we are trying to do with the data. Because for every test that we do, we have a different procedure, we have a different protocol. It becomes also complicated to have data that are harmonized, but we cannot go too far from the reality. So there are some tests that can be standardized and can be done always in the same conditions. In some other cases, unfortunately, we cannot do that. So we have to take this in consideration. So here I'm jumping a little bit to the part of what we want to assess of a material. So there are many properties that the material has, as I said. Some properties are more important, others will be less relevant, maybe optional, others absolutely relevant. So when we are starting to make the protocols for the characterization of the materials, we have to consider from the beginning what is absolutely relevant that we have, what are the characteristics that have to be there, what are some characteristics that can improve the material, but if they are not there, we can survive with that, and if there are properties that we don't need to care about. Once that we have this, what we have to do is to think about the methods that we have to use. So we have to standardize, if possible. If it's not possible, we have to build a robust protocol for assessing the performance. And assessing the performance means that we have also to establish some values that are acceptable for the material, because especially for the industry, many times we can make tests that are just a comparison between materials. At flow TRL level, it's something that can be done. But if we go to the industrial level, there are some criteria that have to be established and have to be reached. Otherwise, the product will not be sold. So we have to think about this. And this is maybe that now I will be I will be attacked by the people that make multi-criteria decision analysis. But what we have to evaluate, we have to establish which are the leading parameters. Because if there are some parameters that are extremely important, they don't have the same weight of the others. Sometimes we can decide just, okay, these are the leading parameters. I will take the solution that have the best performance on this. In some other cases, maybe that we can mediate between the parameters, can give more importance to some, less importance to others, and so to make a final conclusion that can also be automatized, but with this assumption. But we have to decide. So the industrial partner, in this case, in a project, is very important because he knows the market, he knows what he wants, so he has to participate in this. So, another jump. Sorry, but it was difficult to see everything without jumping from one side to the other. So, well, we are a researcher. We know that there are different kind of approaches according to the level of development of the material that we have. So I divided in 3 ranges, but the NASA did it in 9. Very complicated so, to understand where we are sometimes. But well, it goes from fundamental research, where we have some characterization methods that are very simple, to the high tier level, where we have a huge kind of system for characterization. So normally for low tier level, what we are looking for is like to understand the structure of the material, its morphology, the chemical composition of how the material is done, and then some basic properties like thermal, mechanical. Here I've already talked about some characterization method that could be used. So when we go to a little bit higher TRL, then we start already to have, well, also the production of the material is a little bit easier because the developers have already started to scale up a little bit the system, so we have more material, and we can start to make some more complicated tests. So we can age the material, can start to work in conditions that are close to the real conditions, can even make some component level tests. The big part arises when the material is very developed, and we can go really, well, in this case it's the industry that leads the development, and we can go to scale up the system to the real conditions. You have to consider that the price that we will pay for the characterization goes up when we are going to higher tier level. Just to build a structure like that ones that you are seeing will be very expensive. It will cost maybe even, well, not in the case of wind turbine, that is the test bench on the left. The wind turbine will cost more, but anyway, you can imagine that it's not just 10,000 euros of test. So, well, we are talking a lot about characterization, but nowadays we can also assess the functionality with other means. So we are lucky that we live in modern ages, and we have also some models that can help us with the characterization. There are different kind of models that can follow us with the development at different tier levels. So we can go from quantum system, quantum computational system, like what we saw yesterday during the training with CHIASMA, so that can give us some information about the material in the initial phases. So sometimes it can be even easier than developing the material itself. So we can already get some inputs from the beginning. And when we go up with scaling up the development, there are other kind of instruments that can help us. Well, this is like a tool that we have, but it's complementary to the characterization, because each characterization modeling system has to be approached also with characterization, because there are inputs that the model can need in some cases. In other cases, the models need to be validated. So we are talking about something that goes in parallel, that doesn't go separately, but modeling and characterization have always been together, so that we can develop the material in the right way. So, well, I don't know how I go with the time, but I'm almost done, and I want to talk about what I think that is interesting, because the inputs that the material characterization can give also to the LCA, for example. So there are, I put an example because I think that it's easier, and this is an example that is close to my work, so that I know this better than other kind of characterization methods. So, well, I work in tribology, where we study the friction, the interaction between surfaces, what produce friction, what produce wear, well, also if there is corrosion, all this stuff. So the lubricant is one of the things that we see a lot. And for example, if we are talking about an offshore wind turbine, it uses a lot of oil. And the oil, as we saw before, has many implications. So it is used to reduce the friction, to extend the life of the components. It's also used for cleaning the system, because it's a fluid. So there are a lot of, but let's focus just on the part of reduction of friction and the extension of life of the components, because I think that for the LCA is something that is very useful. So, well, I stole this slide from Mattia Costamagna that presented this. So, well, I'm sorry if I did it without permission, but I think that like this we can see exactly in which part we could be useful for the LCA. So, well, we are reducing friction. Friction means energy, because every time that a system is generating friction, this friction is consumption of energy. So we have to take into consideration that if we are comparing different lubricants, it's not just that we see the life of the lubricant and that's it. We have to consider also into the system that there is this reduction of energy consumption that is being generated. And this data, it can come from the experiments. It's not something that you can have without experiment. And the same goes for the extended component life. If we have if we have a gearbox, it's made of many gears. For a wind turbine, they are gigantic gears. And so if we are prolonging the life of these gears are a component that is in close relationship with the lubricant. So we have to take this in consideration. If I have a failure of a wind turbine, the cost is huge because there is a lot of maintenance that I have to do. You can imagine, I have to dismantle this huge gear and have to replace it. The turbine is not producing energy for a long time. So are we taking into consideration this when we make an LCA? Because we should. So, and this is an example. So can we predict the life duration? Can we predict the friction reduction? Well, we cannot, I will be sincere, we cannot do it exactly like it is, because we can run experiments at low TRL level, maybe that we can go higher. In some cases, we can go even to very high level, like what we have seen with this system, but it takes time. But anyway, we can make a prediction that it has uncertainty, but they are data that I think that could be anyway useful when we are assessing a material at low TRL, because otherwise we are absolutely forgetting about some parameters that can be fundamental. So I'm almost finished. Okay, so well, and so in laboratories we have a system for doing this. Normally what we do is try to scale up the system. So actually we cannot be sure that the friction coefficient in the gearbox of a wind turbine will be what we are assessing. But we can make some estimation that can have some errors, but it's better than nothing. So I was talking about this for the lubricants because it's closer to my case, but we have another use case that is the sunscreen. Also there, we have the same situation because, well, we are assessing the sunscreen, all if they are the same, we make the parameters, we see some parameters for the LCA, but actually one sunscreen, if I go in the sea, will disappear. So I have to put more. So it's they are not working in the same way. So if I'm putting more, also the hazard that I'm assuming is higher because it's increasing the amount that I will absorb. So they cannot be put on the same level because there are some parameters that have to be considered separately and weighed by the functionality that I'm giving to certain properties. So, and I have also for the part of textiles, of course, so that we have the 3 use cases. So a textile in itself can be more or less sustainable, but we have to see also what is the duration of the textile. Because, and we have to consider also in the life cycle that if a textile will last half of the life of the other, they are not on the same scale. So we have to consider all these parameters. So well, thank you.
Okay, so thank you, Francesco and Jonander. And is there any questions in the room? Yeah.
Thank you. I really thank you so much for this great presentation. So it cost me last 20 years of work from minimum quality lubrication coatings to barrier coatings for hydrogen embrittlement, and now, yeah, the last example on textile, we are working from the European Commission on that. Yeah, it's a comment more than a question because we can add more to what you both really presented. So great presentation. And the point related to fair data, yes, okay. I would like to underline that standards are not always there. Sometimes we are facing some really new challenge. The important thing for data collection is to describe as much as possible the context, in my point of view, and what numbers represent. That's really close to the ideal FAIR data because other people can use them. And the scoring as well, I mean, it's not bad as it is, as such. But if we find out a way to communicate with others and to say, okay, my scoring represents this number because it's the algorithm to produce that is such and such. I think that would go in the direction of data accessibility, reusability, and interoperability somehow. So, thank you again.
Well, I don't know if, can you hear me? Okay. So, well, I agree with you. I think that, well, we are in a phase of transition for what is the characterization. I think that most of us, like people working in characterization, are not still aware of the importance of these aspects, but we need to run in that direction because artificial intelligence is there. We need to produce data that are as reliable as much as possible. So I completely agree with you. I think that there are also some tools that are starting to be developed to help also the scientists, because sometimes you are running from one test to the other. You don't want to take note of the humidity of the laboratory all the time, or and these are all important conditions that sometimes are not considered but can influence a lot the test. So I think that now, for example, with electronic laboratory notebook, there are some initiatives that I think that is important that the laboratories start to implement, because we need data, reliable, and well, we are working in this direction also with like connecting the processes with the characterization. So, you know, we are creating an infrastructure where all the data of the process will directly go to the database, internal database, and the characterization as well, so that you can associate all the steps of the production until the characterization, and this is something that needs to be done.
Okay, so if you don't mind, so we don't delay too much, we can continue the discussion during the coffee breaks. So I would like to introduce the next speaker. She's Lisa Pitzel from Green Decisions.